Okay, so I welcome everyone to the ninth week of the live online live tutorial session for the course linear algebra. So today we'll be discussing some problem related to quotient spaces, which is the content of the ninth assignment of this course. So I'll start with some basic definition and theorem which we'll be using today. So again, the first assumption is V is a finite dimensional. Suppose V is a finite dimensional vector space. It is not needed. Actually, it's not needed. So okay, just not finite dimension needed. Suppose V is a vector space. Space over a field K, and U is a subspace of V, and U subset of V is a subspace. Subspace mean again the vector space operations are like that if we restrict the vector space operation on U, that is an well defined operation, vector space operation. So this is a subspace of V. Okay, and then we define the quotient space. So just a minute. So then the quotient space is quotient space V mod U is defined as V mod U equals all elements like of the form V plus U. So what is this? This is like translating, this is a set like isomorphic to or homeomorphic to U itself. Just I am translating each element of U by V. So that is the notation U, V plus U. So this runs over V belongs to V. So this is the set, and on this set, if I define like this is sometimes also this is notation for V bar. So this is an like the if I define an equivalence relation on V as like, so this is basically also written as V mod tilde U, where like A tilde U B if and only if A minus B belongs to U. So this is the relation. So with respect to this relation, this is the class of that. So this is an equivalence relation, and with respect to this equivalence class, this all the equivalence class is taken as the quotient space V mod U. Okay, so this is the definition for quotient space, and this is a vector space, again a vector space. So V mod U is a vector space over some field K, and if my V was finite dimensional, so if dimension of V is finite less than infinity, then I can say exactly what is the dimension of, so then dimension of V mod U, this thing is dimension of V minus dimension of U. This is again follows from the rank nullity theorem, because we have a map from V to V mod U, just the sending V to V plus U, that means V bar. Okay, that like that is an onto map, because any element is of the form v plus u, so I can take the preimage as v belongs to v. So that is an onto map, and the kernel of that map exactly equals to u. So by rank nullity theorem, you know that for a rank of that map, so it follows from this. So there is projection map y from v to v mod u, descending v to v bar. So it's an onto map, onto linear map, onto k linear map with kernel of pi equal to exactly u, because if anything is 0 in v mod u, that means that element must be belongs to u. That is follows from this equivalence relation, right? So from there, using the rank nullity theorem, or the rank theorem, we get that this dimension of v mod u is dimension of v minus dimension of u. Okay, so another thing, okay, that we don't need anyway. Okay, anyway, another thing is the codimension. The codimension is defined as follows. Again, for the codimension also, we don't need exactly the finite dimension, but in finite dimension it will be like precisely. So codimension, dimension of u in v is denoted by codim of u comma v, and defined as codim u comma v equals to the dimension of the quotient space v mod u. Okay, and in finite dimension, this is equals to dimension of v minus dimension of u if dimension of v is finite. Okay, so this will use in the in one problem, that what we mean by codimension of a subspace in a vector space. Okay, so that's what we need at least for today only, and rank theorem probably somewhere. Okay, so let's go to the this is a very easy question. So you are given u and w are two subspaces of v with u contained in w, and if w prime is a complement of w in v, so again the complement we have discussed in previous tutorial also, that this complement means w prime plus w, w prime direct sum w is v. Okay, and then you need to show that u plus w prime, that is a subspace and obviously contains u, so that is a complement of w mod u in v mod u. Okay, so what we are given, u contained in w, so I can think u as a subspace of w also, so then w mod u is well defined in that sense, and w prime is complement, so given w prime direct sum w equal to v and u contained in w. Now u plus w prime, this is also so u also contained in u plus w prime, so that gives me this u plus w prime mod u as a subspace of w mod as a subspace of v mod u, right? Because u plus w prime is a subspace of v again, so that is a subspace of v mod u. and also w mod u is also subspace of v mod u. Now I need to show these two are complement of one another. That means to show need to show u plus w prime mod u, like this direct sum w mod u is v mod u. Okay, so this we need to show. So any idea how to show this one? So first we need to show anything is direct sum. First we need to show this intersection is like 0, and then it is a sum. That v mod u we can write as sum of these two spaces. Right? So is it clear that the intersection between these two are 0? If we just analyze this one, that u mod w prime mod u, so you actually can see that u plus w prime is nothing but like it is conceived in w prime also. Just I take u so that the quotient makes sense, because I immediately don't know that whether u contained in w prime or not. Right? If you don't contain in w prime, then I can't define the quotient space, right? So for that reason I took this u plus w prime mod u, but in the quotient, when we pass to quotient, it is nothing but w prime mod u just, right? And you like to define the quotient, we need only this u plus w prime, but in the quotient it is nothing but, like, if I just write it, u plus w prime mod u, this is like an equivalent anything. This is gets to if it is well defined, w prime mod u, it is not well defined that way, but you can like this quotient u always kill the u part here. Okay, so that's the whole point of this one, that this is indeed the direct sum of these, due to this w prime direct sum w equal to v. So if I take the w prime direct sum w mod u, and that is exactly v mod u, right? But how it is split? W prime direct sum w mod u, that I somehow want to identify with this. W mod u is fine, and I will send the remaining things as u plus w prime mod u. Then it is clearly like that way you get this direct sum. Now for the first why this is, let's see why this is intersection is phi. So suppose let something x mod u, this belongs to u plus w prime mod u intersection with w mod u. Okay, so or I can just write it as x bar. Okay, x bar. Now x bar belongs to this intersection, this means, so I can so x equal to will be some u plus w prime, and this belongs to where okay, I should write in that form. So once this is the case, then like x plus u equal to would be some u plus w prime plus u, and that is equal to some w plus u. Like these, all these things are in different class. So this is an element, so u belongs to u, w prime belongs to capital W prime, and w belongs to w. So so belongs to here means I can write in, I have a representative for x as u plus w prime and w, right? So that this I can write, but from this relation what we get, like I want to show that this x, if I can show that this x belongs to u, then I'm done. But from here, if these two classes are same, then by the equivalence thing, two things are same if and only if this u plus w prime minus w, this belongs to u, right? So u plus w prime minus w, this belongs to u. And u, I know u as a, u belongs to, like u is a subset of w, as a subspace of w. So and so this means that, and w prime is an element of this capital W prime, and w intersection w prime is 0, right? So another thing is, so I can just write it in the form like, so take this as some u1 belongs to u, so then w prime equal to u1 plus w minus u. All the things u1, all these things belongs to u1 w, all this belongs to w, right? But w prime belongs to my w prime, so this actually belongs to w intersection w prime, but w intersection w prime is 0, so this implies that w prime equal to 0. Once w prime equal to 0, so this total u plus w prime plus u is nothing but 0 plus u, so that means w belongs to u, or rather just x belongs to u. Once x belongs to u, x bar equal to 0. This implies that x plus u equal to u plus capital U, and u plus capital U is nothing but 0 plus capital U, and this means that x bar equal to just the class of 0, right? So so that implies that the intersection is only 0. Now for the direct sum is again I have to use this thing. So for I know that any element of V, so if I pick any element V from V, so I will take V belongs to V bar belongs to V mod U. Now I know that this V is a direct sum of W prime plus W, so this implies there exists W belongs to, like as this is a direct sum, so there will be unique W belongs to W and W prime belongs to capital W prime, such that V equal to W plus W prime. So now you just consider these two class, like class of W, and then V bar equal to clearly W plus W prime bar, but as this is a vector space, like V mod U is a vector space, so this is clearly W bar, just from the vector space like vector space addition thing, this is nothing but W bar and W prime bar. Okay, so for each element I get an like representation such that V bar can be written as W bar plus W prime bar. So that means, and this W prime bar, this clearly belongs to U plus W prime mod U, and W bar belongs to W mod U. So this is a direct sum also due to this intersection is 0. So from the both thing we get that this is a this d plus w prime is complement of w module. So is this clear?
Yes, sir, clear.
Okay. So okay, then let's go to next question. So here you are given that f is a k-linear operator on a vector space V. That means it is just a map from like linear map from V to V. So here they given that is k-linear. Now we need to show the following statement are equivalent. Okay, so first statement says that F induces an isomorphism of image F. Okay, so first one, what it says that F induces automorphism of image G, right? So that means F restricted to image of F, that means I can simply write it as like F of V, image of F is nothing but whole image of under V. So just let me write that. So it is restricted to F of V. So then it is a map from F of V to F of V, because this is an automorphism it is saying. So map from F of V to F of V, but also automorphism means this map is an isomorphism, right? So is an isomorphism. Is an isomorphism. So this means like three things it means. First of all, if I like take any element f of v, small v, so that is an element of f of v, and if I map it under f, so that goes to f of v. So that is clearly an element of f of v. So this is not an like issue. So this is and I can define and will define like k-linear map from f of v to f of v. But this is an isomorphism. So what it means that kernel of this map is 0, and also this is surjective. So injectivity. So injectivity of f restricted to f of v implies that kernel of f restricted to f of v is 0. But what is the kernel of this restriction? We have used this many times, that kernel of restriction is nothing but original like kernel of f, the original f it is given, restricted with like intersection with f of v, that is the kernel. So that is 0. That means kernel f intersection image f is 0, right? So I just for the thing that this is, so this I wrote like two things, but it is, you can think just as like this is just image f. So I'll just replace it as okay, let it keep like, so kernel f intersection image f, this is 0. So this is injectivity implies. What is surjectivity here? Surjectivity means if I pick any v belongs to v and consider f of v, then I will get another element from v, say w, such that f of v equal to f of w, like f of w equal to f of v, right? So that's what surjectivity of f restricted to f of v implies that for each v belongs to v, there exists w belongs to v, such that f of v, which is an element of image of f, that will be equal to f of w, right? f of w. That is just the meaning of this surjectivity, right? Now this is the whole statement, like f induces automorphism this. Now what this will imply, so I need to show that it should imply that f induces an automorphism of v mod kernel f. Okay, so now let's go to the second one. So again, f induces this means that I have map from f of v to v, and kernel f I know that is a subspace of v, right? Is a subspace, right? Now I can consider v mod kernel f, and f induces means I can define this as f bar from this to v mod kernel f, just sending like v bar, that means v bar's kernel f. I'll just send it to f v bar. So for when I'm defining this, I should this map should be well defined. So well defined, what it means, if I take take two representative for this v, suppose v1 and v2, such that v1 bar equal to v2 bar, then under f bar they should go to the same element here, right? So so that is easy to see, because f bar of for v1 bar equal to v2 bar, so v1 bar equal to v2 bar, that means that this v1 minus v2 belongs to kernel of f, okay. We have v1 minus v2 belongs to kernel f, but this belongs to kernel f means f of v1 minus v2 equal to 0, so that means f of v1 equal to f of v2. But once f of v1 equal to v2, then clearly that will imply that f v1 bar equal to f v2 bar, and f v1 bar, f v2 bar, what are they? They are just f bar of v1 bar, right? And this is f bar of v2 bar, right? So this is by definition. So this implies f bar is well defined, but this is in general actually true. You don't have to in general it is true whenever you have such map. Okay, so f bar is well defined map. Now what we need to show, that this is an isomorphism, right? This clearly belongs to kernel f, I can just send it to that, so there is no problem. Only I need to show that kernel of, for the injective, I will show f bar is injective as well as surjective. So for the injectivity, I need to show kernel of f bar equal to 0. But what is kernel of f? This is all v bar such that f v whole bar, this is 0, like 0 bar, right? And now f v bar equal to 0 bar, that means f of v belongs to kernel f, because that's the relation here. So this means that v bar, so v bar again I'm just thinking here only, so that means f of v is belongs to kernel f, and f of v belongs to kernel f, that means f of v equal to 0, and okay, so v bar such that f of v, this is 0. Now if we assume this statement, first one, that this is an isomorphism, then I know that kernel and kernel of f and image of f intersect only at 0. And what we get here it says that f of v which is an element in the image of f, that is lies in the kernel of f also, right? So this I can again further write as v bar such that fv belongs to like image f. Obviously it belongs to image f, and now this condition implies that this is also belongs to kernel f, right? But this is 0, so f of b must be 0. Once f of b is 0, then again this f of b, again I can say that like this again implies that this is 0, that not 0. If we assume the first statement, then this is 0. Okay, this is fine. This is kernel of f bar. And what will be the like inverse image I should take? So suppose if I take any v mod kernel f, so then I should use the surjectivity of here, right? So suppose I consider v bar, then I should get a w such that f of w bar equal to v bar, but that is again true by this surjectivity. Okay, so now let us just, so for the surjectivity, or just let us assume first one. Okay, so 1 implies 2. How do we show this one? So 1 implies, so their image of f intersection kernel f, so this is again g. Okay, so image of intersection kernel f is 0, so this implies that kernel of f bar equal to all v bar such that fv equal to 0. But fv equal to 0, that means again that all v bar such that v belongs to kernel f, obviously, because fv equal to 0, intersection with image f also, because fv is how do you say, so this is again image f, because this is like v is an element again of here. So fv belongs to image of v, so I can take an w such that f of w equal to v, right? Or we don't need that also. Okay, v is kernel f is good enough, right? So yeah, it will not belongs to image f, sorry. So this belongs to kernel f, but v bar is so once v belongs to kernel f, v bar is just 0, right? So this is contains only 0 bar, because I am considering v mod kernel f itself. So this is kernel f bar is 0, that means f bar is injective. Now let's prove the surjectivity of this f bar. So let some v bar belongs to v mod kernel f. Now I need to find an w, but for this one again I will use the previous surjectivity, right? So for f of v belongs to image f, by surjectivity of f restricted to f of v, that means the image, there exists w belongs to v, there exists w belongs to v such that f of w equals to f of v, right? Now, so now what will be the choice of some w such that this f of f, that will be this. So this is simple, right? So So take f w bar and belongs to v mod kernel f, and f of f bar of fw whole bar, what is that? That is nothing but f of like this is my whole thing, so f of w whole bar, but f of w is nothing but f of v, so this is nothing but fv bar, and that is again same as f bar of v bar, right? So okay, did I miss something? So I should get one w such that f bar of w bar equal to v bar. So I want f bar of w bar equal to v bar. That means fw whole bar equal to v bar. Okay, did I miss something? Okay, fine. Oh, yes, this is true, but I want something else. W should be my pre-image. So from here actually, so it is easy to see that W should be my pre-image, then I can only say this one. So this means that f of v minus f of w, this thing equal to 0 simply by linearity of f. Okay, and this 0 means that v minus fw, this belongs to kernel f. Then again, as by the definition of the relation and quotient, so this means that v bar equal to fw bar, and fw bar, that means f bar of w bar. So we get by the surjectivity of f restricted to fb, an element like surjectivity of f bar. So this implies f bar is surjective. Also, the conversely, if I assume that this map is automorphism, that means this is isomorphism, then again in this case also kernel of f bar will be again like what is the kernel of this map. So all those so this is equal to 0, right? That means that fv, so fv all those, yes. So okay, so now let's see, 2 implies 1, that f bar is injective implies that this thing is the kernel of f bar is 0. That means if implies if f of v belongs to kernel f intersection image f, then I should have v belongs to this, v bar is 0, right? Then v bar is 0 means v belongs to kernel f, right? So from here like I need to show the injectivity of this one at least. So for this one I need to show that kernel of f intersection image of f equal to 0. But if v belongs to kernel f, then f v equal to 0. So this okay, the converse way is okay. So this saying that f of v equal to 0 if and only if like v belongs to kernel f. This is the case, right? So fb belongs to image of f. That means f of b equal to um, some f of w, and this also belongs to kernel f. That means if I take f of v, that belongs to like that is 0, right? So f of b clearly belongs to image of f, so that is not a problem. So I can take just w equal to v. So that's the important part, that f of b equal to 0 if and only if b belongs to kernel f. And what that means, that exactly means that if like um, that is that if I take kernel of f intersection with image of f, that is 0, because if I take anything from here, then f of v will be 0. That means like okay, so if I take v belong like some say w belongs to here, then f of w equal to 0 and w equal to some f of v, right? Now just plug it here, then w belongs to like w equal to f of y, so f of v equal to 0. That means v belongs to kernel f, and v belongs to kernel f means f v equal to 0. That means w equal to 0. Clear? So so this precisely implies that this is equal to 0. So this means that f restricted to fv is injective. Is this clear? So this exactly implies this one. So just pick an element w belongs to kernel f intersection image f, and see that as w belongs to image of f, so there exists some v such that f of v equal to w. Now w belongs to kernel f, so f of w equal to 0, and w equal to w equal to f of v. So f of v equal to 0, and whenever you have f of v equal to 0 from this injectivity, I know that v belongs to kernel f. But by our choice, w is f of v, so and v belongs to kernel f, so f of v equal to w equal to 0. So from there I get this one. And for the surjectivity again, so for the surjectivity, what I need to show, that if I take any element from v mod kernel f, so I need to show the surjectivity of this f restricted to fv, right? The surjectivity of this one is given. Okay, so let f of v belongs to image of f, and then I know that this map is like surjective. This map is surjective means if I take any element v mod kernel f, that has a preimage. Now but in our case, so I can consider just f v bar, then consider this map f v bar. This belongs to v mod kernel of f, and then okay, so kernel of f, and by surjectivity of f bar, there exists w bar belongs to v mod kernel f, such that f bar of w bar equal to fv whole bar, and f bar of w bar, that means that fw whole bar equal to fv bar. Okay, Probably I missed something here. So I should consider instead of, yes, I'm not getting anything new, so okay, I should consider V itself. Let it be belongs to, and V bar belongs to this. Then by surjectivity of F bar I will get W bar such that F bar of W bar equal to, yes, equal to V bar. That means F bar of FW whole bar equal to bar equal to V bar, and if two bar is same, that means V minus FW, this belongs to kernel F, right? That's the equivalence relation here. So this means that F of V, which I take here, should be equal to F of W. So this W is the required like preimage. So this implies F restricted to F of V is surjective, because I get an element FW in the image of F such that F of W equal to F of V. Okay, so this is surjective, so hence F restricted to F is an isomorphism. Now let's so we prove one if and only if two. Now for the three part, from the one we just seen that if F is like injective, then kernel F intersection image F equal to 0. So that implies that if V equal to just sum image F plus kernel F, then it is just like direct, it will be direct sum. So enough to show that image F plus kernel F equal to V, just plus. So again that plus will come from the surjectivity, right? Okay, just let me write that. So one if and only if 3. So how do you get that? That 1 implies that kernel F, so because kernel F intersection image F equal to 0 if and only if F restricted to FV is injective, right? Both of you will get this, because exactly kernel of F restricted to FV is equal to this, and this is like the direct sum requirement. And other thing is for the surjectivity, okay, for the surjectivity I know that for each V belongs to B there exists W such that FV equal to F of W, right? So if I pick a element V belongs to V, then I should be able to write this as an element of image F plus kernel F. But the forward part, say you write, okay, V belongs to V, and then F of V, this belongs to image F. So surjectivity will imply surjectivity of F restricted to FV implies that there exists W belongs to V such that F of W equals to F of V. That means V minus FW belongs to kernel F, and say that element is some U, that means V equal to U plus FW. Clearly FW belongs to image of F, and V by our choice is belongs to kernel F. So I write any element V belongs to V as sum of element of kernel F plus image F. So that proves that F restricted to FV is isomorphism, implies that this is a direct sum. If I can write V as direct sum of kernel F and image F. For the converse part, again, if I assume that V is direct sum of kernel F and image F, so if V equal to kernel F plus image F, then I should be able to show that this F restricted to F is surjective, right? So then for any V belongs to V, consider FV that will belongs to image of F, and I should be able to get an W such that F of V equal to W. But from this representation, I know that V equal to some U plus F of W for U belongs to kernel F and W belongs to V, just from this direction. But what that implies? That implies that F of V equal to F of W. So this implies that F restricted to FV is surjective. Right. So this concludes the proof of 1 if and only if 3. Right. And the last one is again just a variant of just a like 3 prime kind of, because it is saying that kernel F has a F invariant complement W such that the restriction F restricted to W is an automorphism of W. Right. Now F invariant complement means if I take like F, suppose the complement, this complement is W, if I restrict F to W, then that is a map from W to W, and that is a that is just a map from W to W. And moreover, it is saying that restriction F restricted to W is an automorphism of W. But we have just from this relation, if I just we just show that like 3 if and only 1. So if I have this V equal to image F plus kernel F, then I know that F restricted to image of F is an automorphism, and already kernel like image of F is a complement of this kernel F, because kernel F plus image F is V. So this is the required W. So I just take W equal to image of F, then this everything follows. So 4 is just a combination of 1, 3. Okay, so this completes the whole problem. So is there any question here?
No, sir.
Okay, so then just give me 5 minutes. I'll just briefly explain the next problem, and then we'll stop. Okay, so it is given that U1, U2, Un are finite co-dimensional subspace. Co-dimensional again means that if I take V mod Ui, that is finite. The dimension of that thing is finite, right? And U defined to be the intersection of all those Ui. And we know that intersection of any number of subspace, that is again a subspace. So U is again a subspace. And further you consider Ui prime, so we will not use this Ui prime. So let me just I don't need this one. So just consider this U. Now we need to show that U is finite codimensional. That means we know that for dimension we know that dimension of U, because this U is already contained in each Ui, right? Each U is contained in U is being the intersection of all Ui, so that is a subspace, and that is a subspace of each Ui. So if Ui are finite dimensional, at least one of them is finite dimensional, then U is finite dimensional. But in this case you are given that Ui's are finite codimensional, so then also the intersection will also be finite codimensional. and exactly the finite, like the codimension will be like restricted by the sum of the codimension of all of the ui. Okay, so this is about the so first one. But again, codimension of u in v, so this is equal to the dimension of v mod u, right? And u is the intersection of all those ui, so this is dimension of v mod intersection of ui. Now you have a like okay, so this I'm claiming that this is less equal to sum of dimension of v mod ui equal to 1 to n. That is enough. But for this thing, if I can so see that, so just consider this map v mod u to like direct sum of v mod ui I equal to 1 to n, this map, and this is exactly like intersection ui. So what you could do, what just send x plus u, this element, to x plus u1, x plus u2, all the way up to x plus un, this thing. And this is an well defined map, because if x1 plus u equal to x2 plus u, so that means x1 minus x2 belongs to u, and that means that x1 minus x2 belongs to all of u1, u2, un, right? Because this is the intersection. Now if x1 and x2 is all of the u1, u2, un, then x1 plus u1 is equal to x2 plus u2. Similarly, x1 plus u2 equal to x2 plus u2, and so on. So that will give a so this is an well defined map. And like the dimension, now comes the dimension thing. So if this map were like onto, so just like again you just apply the rank nullity theorem here. So dimension of v mod u, so this, suppose this is G map, the dimension of this, I know this dimension of the kernel f, dimension of kernel f plus dimension of like image of f, G of v mod u. Right, now what is this kernel of f? It is like this, I can so G mod u, if it were onto, then like then it will be like just direct that. So what will be the dimension of this v mod ui? So G of v mod I is a subspace of v mod ui, and the dimension of this space is sum of dimension of v mod ui. And if it were onto, then I would have get that this is the whole thing, kernel f will 0. So this is exactly bounded above by the dimension of the direct sum v mod ui, and this dimension equal to the sum of dimension v mod ui. So this is this is the like case here. So that's how it is bounded above. And now if you have the equality, then from this map also you just directly see that if you have this equality, then that will imply that this map is an isomorphism. Because what is the kernel here? If you see the kernel, sorry, this I wrote as f, this is G. This kernel of G. Kernel of G exactly. So all those element x plus u such that belongs to u. That means x belongs to u1, x belongs to u2, all the way x belongs to un. That means this kernel of G, this is nothing but 0 only. like just 0 bar you say. Okay, so that means this G is just an like injective map, so that's why this dimension of kernel of G, this is 0. So whenever G is on 2, you have this is equality, and if you have the if you have the onto-ness, then you have this dimension and this as isomorphism. So that concludes this one, and for the this part ui plus ui prime equal to v, you just consider this map, again consider this map you know isomorphism. So for any v belongs to v, you consider like for the ith place you consider v plus u1 all the way up to 0 plus ui. So only on the 0 ith part you consider 0, and all the other part you just consider like v plus uj. Okay, un, sorry. So this thing, so this map being onto, so it has a pre-image, so just using that thing you can actually claim that this happens also, and also conversely. Okay, so it's already a bit late, so I'll stop here, and if you have any other question you can discuss, or otherwise I'll write this thing clearly and upload in the description box. So um, do you have any other question?
No, sir. Thank you.
Okay, then we'll stop here, and we'll meet next week again. Thank you.